Okay, lesson 7. We'll do a few more examples where we're going to sketch some curves by finding all those characteristics that we did yesterday. So the first one's already in factored form for us, which makes it nice. And because there are no denominators, it's not a radical function. There are no restrictions on x, so our domain would be all real numbers. We can find our y-intercept by letting x equal 0. So that will give us 0, because the first factor will be 0 squared. Doesn't really matter what the second factor works out to. So this graph will go through the origin. That will also be one of our x-intercepts, but that's not the only one. And again, the nice thing that it's because it's in factored form, we can see that x equals 0 is one x-intercept, but because that factor is squared, remember that means it's a multiplicity of 2. And if you remember from 30-1, that means the graph will bounce off the x-axis there. And the same is true for the second x-intercept. Because x plus 2 is squared, negative 2 is an x-intercept, but again, it'll have a multiplicity of 2. Okay? So next we'll find our intervals of increase and decrease by using the derivative. So I want you to differentiate this one, and then we'll check it. Okay, do the derivative. Where?
Yeah, listen, Chad, listen. It took me a minute. It's too early.
So how many of you did it by simplifying first? Because you can do it using the product rule, that works for sure. Or you can simplify it first. So it doesn't really matter. How many did it using product rule? Where's your booklet? We'll grab another one off the counter there. Everyone do it using product rule? Okay. So dy by dx, if we use the product rule, which would be the derivative of the first factor, which is 2x, times the second factor, plus derivative of the second factor, which you have to use the chain rule for. And when you multiply the derivative of what's inside, it'll just be 1 times the first factor. So you can simplify this a little bit. And remember, you're trying to find the critical numbers for this. You're trying to find the zeros of this. And so you want to factor it to get the zeros. And so I would factor it from this point here. There is a common factor of 2x bracket x plus 2. Right? Each term has at least a 2x in it, and each term has at least one factor of x plus 2 in it. And so if you take that out as a common factor, from the first term you're going to be left with x plus 2, and from the second term you're just going to be left with x. So I have 2x bracket x plus 2 bracket, and then that's just going to be 2x plus 2. And because they're all factored, because they're all factored, we can get our critical numbers of 0, -2, and -1. If you let each factor equal 0 and solve for x, that's what you'll have. Those are the critical numbers. Which, again, gives us our number line divided into 4 intervals. By those 3 critical numbers. So, a number in the first interval, a number less than -2. And again, I'm going to use the factored form. When x is -3, the first factor will be negative, the second factor will be negative, and the third factor will be negative. 3 negatives multiplied together to give us a negative, so the graph will be decreasing in that interval. If we look at the original function, it'll be a 4th degree polynomial because the first x is squared. The x in the bracket will also be squared, which will give us an x to the 4th. It'll be a positive 1x to the 4th will be our first term. Because the degree is even, it'll act just like a quadratic with an initial coefficient that's positive. It'll open upwards. This graph will rise to the left, rise to the right, and that is if you're going right to left. So if you're going left to right, it'll fall in that first interval, which we've just confirmed actually happens. So next, what about between -1 and -2? A number like -1.5. The first factor will be negative, the second factor will be positive, and the third factor will be negative. 2 negatives times a positive gives us a positive, so the function will be increasing in that interval. Between -1 and 0, something like -1/2, again, the first factor will be negative, the second factor will be positive, and the third factor will also be positive. But 1 negative times 2 positive gives us a negative, so the function is decreasing in that interval. And in the last interval, a number greater than 0, a number like +1, all 3 factors will be positive, so the function is increasing there. Which tells us that we have a minimum at f at -2. We have a maximum at f at -1. Another minimum at f at 0. And when you let x equal -2 in the function, you're going to get 0. Remember, that was one of our x-intercepts with a multiplicity of 2. When you let x equal -1, you're going to get +1. And 0 is also 0. Again, that's our other x-intercept with a multiplicity of 2. The graph bounces off the x-axis there. Okay. So now we need to find our second derivative so that we can find concavity and any points of inflection. To do that, we would want to multiply out the factors that we have for the second derivative, because right now we have 3 factors. So it would be best to multiply it out. And so what you would get for dy by dx, when it's multiplied, it'll be 4x cubed plus 12x squared plus 8x if you multiply those out. So you're multiplying out the 3 factors that we have for the first derivative, so that now we can take the second derivative. So d squared y over dx squared would be 12x squared plus 24x plus 8. And again, we want to find the critical numbers for this. So we'll factor that out, and there's a common factor of 4 that leaves us with 3x squared plus 6x plus 2. And that quadratic is not factorable. So again, we would have to use the quadratic formula to get our critical numbers. Negative b plus and minus the square root of b squared minus 4 times a times c all over 2a. So that'll give us negative 6 plus and minus. To get the value of the radicand, what's under the radical, it's 6 squared minus 4 times 3 times 2, which is positive 12, all over 6. Now you can't cancel the 6's because you have to be able to divide all 3 terms by the same number. And right now we can't do that, but we can simplify the radical term. That breaks down to root 4 root 3, which is 2 root 3. And so we'll divide everything by 2 now to simplify. And that would be the exact values of our critical numbers. To place them on the number line, we would want to know what they are as a decimal. So negative 3 plus root 3 in brackets, all divided by 3. So approximately negative 0.42. And then the other one would be negative 3 minus root 3 all over 3, which is negative 1.6 approximately. So we place those two values on our number line. A number to the left of negative 1.6, like negative 2. So if I use the factored form, the first factor is positive 4. That's going to never change. When x is negative 2, though, negative 2 squared is 4 times 3 is 12. This will give us 12 minus 12, which is 0 plus 2. Second factor is positive, which tells us that the graph is concave up in that interval. Between negative 1.6 and positive 0.42, oh sorry, that was negative 0.42, not positive. So a value there could be negative 1. So again, the first factor is positive 4. When x is negative 1, negative 1 squared is 1 times 3 is 3. Take away 6 is negative 3 plus 2 is still negative 1. So the graph is concave down in that interval. A number to the right of negative 0.42 could be 0. And when that happens, both factors are positive, so the graph is concave up there, which means we have inflection points. At those two places. And so if we use the negative 1.6, the value of y works out to be positive 4 over 9. And it's actually the same when we let x equal our negative 0.42. It also works out to be 4 over 9. So again, you'd want to use the exact value in the equation, not the rounded one. Using the exact value gives you these 4 over 9 y values. So we now have everything we need to sketch our graph. Bless you. So again, we have x-intercepts at 0 and negative 2. They both have multiplicities of 2. The graph bounces off the x-axis there. We have a minimum at negative 2, 0, which we already have, as well as 0, 0. Our maximum is at negative 1, 1. Our points of inflection are negative 1.6, 4 over 9, which is just a little bit less than a half. So negative 1.6, a little less than a half, approximately right there. And then at negative 0.4, same y value. So those are our inflection points. So the graph comes down to that minimum, bounces off, inflection change there to the maximum, down, inflection change to the minimum, and then it increases after that. So there's the graph of that function. Okay? So here's one that's going to have some restrictions because you have a radical function. To find our domain here, we have to remember that what's under the radical cannot be negative. 2 minus x has to be greater or equal to 0. It can be 0, but it can't be negative. And so, if you solve for x by adding x to both sides, we'll get x must be less than or equal to positive 2. So there's our domain. Okay, there's our domain. So we're going to have that restriction. There's no rational function here, so there are no asymptotes. We didn't talk about that on the last one, but you only have asymptotes if you have a rational function. So, to find our derivative, we would have to rewrite the initial function so that instead of the root of 2 minus x, it's 2 minus x to the half. And we have to use the product rule here. Derivative of the first factor is 1 times the second factor plus the derivative of the second factor, which we do using the chain rule. And that involves multiplying by the derivative of what's inside, which will be negative 1, as well as multiplying by the first factor of x. So we can simplify this a little bit. 1/2 times negative 1 times x is negative 1/2 x, bracket 2 minus x to the negative 1/2. And we want to find the critical numbers for this. Where does it equal 0? And we can take out a common factor. because the factors tell us where the function equals 0. And our common factor here would be 1, because 1 is divisible by 1 as well as by negative a half, but also both terms have a factor of 2 minus x there. And you remember, when you have rational exponents and you're looking for the common factor, you take out the factor that is the smallest, which in this case would be negative a half. And so when you divide that first term by 2 minus x to the negative a half, the bases are the same, so you subtract the exponents. 1/2 minus negative a half becomes 1/2 plus 1/2, or 1. And when you divide this next term, again, we said that the common factor was actually 1 bracket 2 minus x to the negative a half. When you divide 1 by negative a half, you're going to get negative 2. And that's going to be it, because when you divide the 2 minus x to the negative a half by itself, they cancel. So I have 2 minus x to the negative a half, and then 2 minus x to the 1, which is just 2 minus x. Take away 2, the 2's cancel, and we'll have negative x. Pardon me? Oh, I'm sorry. It should have been 2x. Yeah, thank you. So it'll be 2 minus x, take away 2x, it'll be 2 minus 3x then. Let me just check this again. 1, 2 minus x to the half is right, plus 1/2, 2 minus x to the negative a half times negative 1 times x. So this gives us 2 minus x to the negative a half. 1/2 times negative 1 times x is negative 1/2 x. Taking out a common factor of 2 minus x to the negative a half, I'll get 2 minus x. Yeah, that should have been minus 1/2 x. 2 minus x minus 1/2 x. So that second factor will become 2 minus 3/2 x. Because negative 1x take away half x is negative 3/2 x. So our critical numbers will be when each factor equals 0. When 2 minus x equals 0, which is where x equals 2. And that's going to be the starting point of our graph, because we said that our domain was that x is less than or equal to 2. But we'll have another critical number where 2 minus 3/2 x equals 0. So that would be where 2 equals 3/2 x. And if you multiply both sides by 2, you'll get 4 equals 3x, or x equals 4/3. So there's our critical numbers. we have positive 2 and we have positive 4/3. And again, we've already noted that our domain is that x must be less than or equal to 2. So we're not going to be looking at that last interval. So a number in that first interval has to be between 1 1/3 and 2. So we could use 1.5. And so looking at the factors of the first derivative, so I'm going to use that expression right there, and I'm going to let x equal 1.5. So it'll be 2 minus 1.5, which will be positive 0.5, but that's raised to the power negative 1/2. And that's multiplied by 2 minus 3/2 times another 3/2, which will be 9/4. That gives us a negative value, which means that the graph is decreasing in that interval. A number less than 4/3, we can use 0. So 2 minus 0 is 2. 2 to the negative 1/2 is 1 over the root of 2. Still going to be positive. And the second factor will also be positive. So the graph is increasing there, which means that we have a maximum at f at 4/3. And when x is 4/3, you'll get a value of positive 2 in the original function. Okay? So now, the second derivative, we will have to use the product rule here from the first derivative. So d squared y over dx squared. So the derivative of the first factor using the chain rule will be negative 1/2 bracket 2 minus x to the negative 3/2. So that's the first part of the chain rule. The other part is multiplying by the derivative of what's inside, and then multiplying by the second factor, which is 2 minus 3/2 x, plus the derivative of the second factor will just be negative 3/2 times the first factor, which is 2 minus x to the negative 1/2. So we can simplify that a little bit. We've got negative 1/2 times negative 1, which will be positive 1/2. 2 minus x to the negative 3/2 times 2 minus 3/2 x minus 3/2 times 2 minus x to the negative 1/2. And we want to find the critical numbers for this. We can do this by taking out a common factor. Each term, there's only 2 terms here, each term has a common factor of 2 minus x. And remember, when you're looking for the common factor, when you have rational exponents, you always take out the smallest one, which would be negative 3/2. Okay? But we also have a common factor of 1/2, because 1/2 divides into 3/2. So it'll be 1/2 bracket 2 minus x to the negative 3/2, which, if you divide that first term by that common factor, all you're left with is 2 minus 3/2 x. You with us, Brighton? And when you divide the second term, negative 3/2 by 1/2, you're going to get minus 3. 3/2 divided by 1/2 is the same as 3/2 times 2 over 1. And the 2's cancel. And when you divide 2 minus x to the negative 1/2 by 2 minus x to the negative 3/2, you subtract the exponents, keep the base the same. 1/2 minus negative 3/2 becomes, negative 1/2 minus negative 3/2 becomes negative 1/2 plus 3/2, which is 2/2, or 1. So this gives us 1/2 bracket 2 minus x to the negative 3/2 bracket 2 minus 3. Actually, I got to multiply out those brackets first. Gives us negative 6 plus 3x. And so 2 take away 6 is negative 4. Negative 3/2 x plus 3x would be positive 3/2 x. And then we have the minus 4. And we're looking for the critical numbers here. One of those critical numbers will be where this 2 minus x equals 0. But that's where x equals 2, and we already know that that's where the graph is starting. But we still want to use it as a critical number because we want to know whether the graph is concave down or concave up. Our other critical number will come where 3 over 2x minus 4 equals 0, which will be where 3/2 x equals 4, where 3x equals 8, and where x equals 8/3. Now that number is greater than 2. That's 2 2/3. So this is going to be an extraneous critical number. So our only critical number is at x equals 2. If we set up our number line, that's the only number that's going to be on there. Our graph is not valid when x is greater than 2, only when it's less than or equal to 2. So if we choose a number in that interval, let's say the number 0, 2 minus 0 is positive 2. It doesn't matter that the exponent is negative. All that means is that it's going to move to the bottom. It's going to stay positive. The first factor is positive 1/2, which is positive as well, obviously. And when x is 0, the last factor is going to be negative. So 2 positive times a negative is a negative. The graph is going to be concave down. The whole graph will be concave down. So we now have everything we need to sketch our graph. So we're starting at the point 2 comma 0. And the graph is completely to the left of that. We do have a maximum point at 4/3, comma 2. Oops. 4/3, 1 1/3, comma 2 is approximately there. And we have one x-intercept at 2, the other one at 0. The graph is concave down. There's no points of inflection there. So the graph's going to look something like this. And there we go. So this assignment I'm going to collect for marks, page 247 through 10. So I do have some graph paper up here if you want to help yourself to some. But this one I'm going to collect for marks. So we just have one more lesson left that we'll do when we come back. I'm going to send the review down to photocopying right now, and so I can run down and get it and give it to you guys so you have it to take home for the break, because I know you're just dying to work on something.
Besides, not pretty good.
Right? But we're going to be having our test the week after we get back. Okay?